notes. I'll put those links in the chat again. This brainstorm is going into our notes, so that's why I need them open now so that we can get that ready to go. All right, so the question here is determine the frequency, which is the total number of wave cycles in a second. So let's go ahead and take a look at this. We are starting off right here at the start, and I need to figure out how many total waves do we see here. Go ahead and point for me on the board. Where is the end of the first wave? Again, you need a top bump and a bottom bump. Top bump and a bottom bump. All right, purple, you're at the end of the second wave. We want to get to the first wave. There we go. I see purple up there. Let's go, let's go. Get your pointers up there. Thank you. I see red up there. Let's get some more people. Seraphim, Brianna, Alicia, Timothy, make sure your arrows are up there. Kaden, there we go. Thank you, Pink. Yeah, so here is the end of our first one. Awesome. So this is going to be our first wave right here. Where's the end of our next wave? End of our next wave. Point to that one. Beautiful. Yes, here's the end of our next wave. That's number 2. Next wave. Go to the end of our next wave. All right, let's get some more arrows up there too again. Alicia, Noah, Lexi, if you just joined us, go ahead, get your arrows up on the board. Where's the end of our next wave? Absolutely, yeah. So here's our next wave. That's our third wave. And the last wave in 1 second. Last wave in 1 second is right here. Perfect. So remind me in the chat, what's our units here? If we have 4 waves, what's going to be our total, what's going to be our final frequency? 4 waves in 1 second, what's our final frequency? Thank you. I see Cody in the chat. I see Lexi in the chat. Angelina, excellent. Let's get some more participation. Alicia, Timothy, Brianna. Seraphim, Jalen, Kamal, Wyatt. Caden, tell me in the chat. I'm not asking for yeses or nos. I'm asking what is my frequency here? So we know there's 4 waves. Put that with our correct units so that we have our frequency. Awesome. Thank you, Caden. No worries, Lexi. Again, Jalen in the chat. Wyatt. Kamal. Seraphim, Brianna, Alicia, Timothy. Thank you, Brianna. Yeah, exactly. This is going to be 4 hertz, right? Because we saw 4 waves in our second here. Cool. Now the next question is what we learned yesterday, which is what is the period, the time for just 1 cycle to occur, right? So we already identified our first cycle, right, which was right here. And go ahead and tell me, how long did that first cycle take? Go ahead and take a look here. It's halfway between 0.2 seconds and 0.3 seconds. So what do you think that would be? If it's halfway between 0.2 and 0.3, what would that be? Go ahead and tell me in the chat. Well, it needs to be between 0.20 seconds and 0.30 seconds, right? It's literally halfway in between. So what would that be? 0.2 is right here. We need a little bit more. 0.21, 0.22, 0.2. Nope, 0.3 is too far. We're halfway in between 0.2 and 0.3. Yeah, 0.25. There we go. We're getting there. All right, 2.5 would be past a second. So remember, if you want to be between 0.2 and 0.3, between that would actually be 0.25 seconds. Okay, smiley faces in the chat if that makes sense. Okay, because remember, 0.2 is like saying 0.20 and 0.3 is saying like 0.30. So halfway between 20 and 30 is 25. So 0.25. Awesome. Great job, everyone. All right, this is going to be the answer for number 2. Frequency is 4 hertz, but period is 0.25 seconds. You'll actually notice that these are, again, opposites of each other, because if you were to flip 4 and do 1 divided by 4, you would end up with 0.25 seconds. So again, frequency and period are opposites. They are inverses. Raise your hands for number 2. Again, that is our answer. 20 seconds to get our hands raised. Go, go, go.
Everyone. Just a couple of reminders, please don't share any personal information during class. Your participation is still required, and these sessions are being recorded for learning purposes. All right, today is Friday, ending the week off with 1 more lesson here. We're doing things a little unorthodox with the notes right at the beginning, but that's okay. We're going to be learning about frequency, pitch, and sonic booms today. So if you've ever been to like an air show where like a jet flew by, that's what a sonic boom is. All right. Specifically, we will be able to understand the relationship between frequency and pitch. explain the how amplitude affects sound, and explaining how sonic booms occur and calculate speeds in terms of Mach. So like Mach 10, Mach 8, Mach 9, so stuff like that. All right, we already did the notes. So, and the links are still down there if you just entered in the class. Let's look at a brainstorm.
Cool. All right. So what we're going to go ahead and do is I'm going to go ahead and show you a video. And what you're going to do is you're going to observe how the length of the rubber bands in the video is related to the frequency or pitch that you hear. All right. So I'm going to go ahead and grab this video and pop this up on the whiteboard. Oh no, where'd you go? Where'd you go? There we go. All right, here we go. Sharing this with you up on the whiteboard.
Do you know a classical piano or a harp is made of strings of the same thickness but different lengths? Frequency of a sound and pitch depends on the length of the wire being used. The more the length of the wire, the lower will be the frequency of the sound being produced, and so we get a lower pitch. Let us try to understand the effect by a simple experiment. Here we have a box with a rubber band tied around it and two pens. Put both the pens beneath the band at a distance. Plug the band and hear the pitch. It's sharp. Now adjust the distance between the pens to increase the length of the vibrating band. Plug it and hear the pitch. You will notice a difference in the nature of the sound produced as we change the length of the string. The frequency of a sound and pitch depends on the length of the wire used. The more the length of the wire, lower is the frequency of the sound produced, and so we get a low pitch. Wires of the same thickness but different lengths are used to make some musical instruments, and the different lengths give a different pitch sound which creates soulful music.
I always like his wrap up there of soulful music. All right, let's go ahead and talk a little bit about this. So when the wires here, when the wire here was shorter, okay, tell me in the chat, was the sound higher pitched or lower pitched? Higher pitched or lower pitched when it was short right here? Lower, it sounded sharper, right? So think about like voices. If something sounds sharper, is that considered a higher pitch or a lower pitch? Yeah, this was actually higher pitch, right? It was like ding, 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 ding. All right, whereas versus when it got longer, all right, what happened to the pitch when it got longer? Go ahead and tell me in the chat. With the longer length string here, what happened to its pitch? Yeah, it went much lower, right? It was like bom, 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 bom. So this is important to understand, right? That the longer the wire, the lower the pitch, whereas much shorter wires are like this. They're much higher pitched. Okay, now today we're going to take a look at the fact that frequency and pitch are actually related to each other. So let's go ahead and jump into that. I'm going to stop our screen share and go back to our PowerPoints. And bam! There we go. Okay, so let's go ahead and again, what we observed, right, is we saw that longer wire was lower pitched and a shorter wire was higher pitched. Okay, and we're going to see how that's related to frequency today. Okay, so here's the deal. Pitch is how frequency is perceived, the highness or the lowness of a sound. Now, pitch is an observation. So just like you observed with your ears, you heard, right? Oh, that sounds high-pitched or that sounds low-pitched. Frequency, on the other hand, is an actual measurement. Like we've been talking about frequency using hertz and numbers. So frequency is an actual number with a unit. However, they are directly correlated. So this means that anything that is a high frequency also sounds high-pitched, or anything that's a low frequency also sounds low-pitched. Now, to help give you a reference here, generally, I'm not saying always, but generally, female voices tend to be higher-pitched and male voices tend to be lower-pitched. So the same thing is true with frequency. Female voices tend to be higher frequency and male voices tend to be lower frequency. Smiley faces, emojis in the chat, if that makes sense, if you understand that kind of reference point. Okay? Excellent. All right. Now again, frequency has an actual measurement. So it's measured in cycles per second or in those units we learned about, hertz, right? So it's an actual number with a unit. Pitch, on the other hand, does not have units because pitch is just how you personally perceive sound. You personally would say, oh, that's high-pitched or low-pitched. That is not an actual measurement. And as as the guy mentioned in our video, different frequencies produce different musical notes. Exactly what we heard. Okay, now we're going to go ahead and do a quick video here. This is actually a pretty fun video. I'm going to go ahead and just share this one with you on your computer because it works better on your actual computer. What you're going to do is you're going to go ahead and start at the beginning, and you're going to tell me at what frequency do you begin to hear the tone. Then, as soon as you begin to hear the tone, skip more towards the end and identify at what frequency do you stop hearing the tone. So don't play the middle part because the middle part just increases in frequency until you get to the end. So you want to identify where do you start hearing the tone and where do you end hearing the tone, because not everybody hears the same frequencies. I know, these are good videos. Go ahead and really quickly give me a green check, orange X if you understand. Don't watch the whole video. Just watch the start till you start hearing, then skip to the end until you stop hearing. And I want you to tell me in the chat at what frequencies do you start hearing and at what frequencies do you end hearing. And I'll give you my example in the chat. So here we go. I'm going to share the video with you. And again, I want you to actually watch it on your computer because it won't work over my speakers. So audio test, here we go. I'm going to share this with you in the chat. I'll go ahead and give you about a minute to work on that. Here we go. All right, tell me in the chat, what are you getting? What is your starting hertz and what is your ending hertz? So for example, I could start hearing at 40 hertz and then I stopped hearing at about 13,000 hertz. You can probably hear more than I can because you are younger. Yes, awesome. All right, so I see lots of people started hearing at 90 hertz, ended at 17,000. Carlos, you started at 38 and stopped at 18,000. Wow. Lexi, 245 and 18,000. I doubt you should be concerned. It's usually more of a speaker issue. Awesome, Seraphin, you ended up at 17,000. Kamal. Yeah, it's really funny. So one time I was listening to the radio and they were doing this, they were talking about this guy and they were like, hey, so this singer here just sang the world record for the lowest frequency. Let's listen to it. And then I heard nothing, because I cannot hear the lowest frequency that a person can sing. So it was just dead silent. So as you get older, you lose some of your frequency ability to hear. It's called frequency deafness, which for most of us is not a big issue because we don't become super frequency deaf as we get older. But you will be, like, that's why adults usually can't hear those mosquito ringers on your phones. Because your mosquito ringers have too high of a frequency and we are deaf at that point. Smiley faces emojis in the chat if that makes sense. I know, it's pretty cool to think about. Yeah. Awesome. All right, everyone. So that is frequency and pitch. Again, frequency being the measurable thing, pitch being just your observation of it. Now, one other thing we need to go over again is amplitude. Remember, amplitude is related to energy, just like we saw that with ocean waves. Bigger ocean waves hurt more. Yeah, exactly, Lexi. So yeah, I've definitely always had a little bit of a harder time with lower frequencies because I used to have a lot of ear infections when I was a kid, and so I had some hearing issues when I was a kid. So yeah, so maybe when I'm even older, I might have even more frequency deafness, something for me to look forward to. So just like when larger ocean waves hurt you as they hit you, the same thing is true with sound. The larger amplitude the sound, the more energy it has, the louder it sounds. Same thing with smaller, or the opposite with smaller. They have less energy, and so they sound quieter. Now the thing is, though, you can still have the same frequency even if your amplitude changes. So for example, a violin is always high-pitched, okay? And it will still sound like a violin whether or not it's quiet or loud. Okay, so you can actually mix it up. All right, it's not like it's one or the other. It's not like it's low-pitched or high amplitude. You could actually have both of them at the same time. Gotcha, Joseph. Yeah. Oh, wow. Yes. Thanks to your grandpa. Cool. So for example here, you can have a viola that has the same exact pitch. You'll notice that its frequency, its number of waves, is exactly the same. However, its amplitude can change. So you can have a quiet viola with a small amplitude or a loud viola with a big amplitude. All right, or you could change the actual pitch, the frequency, without actually changing the volume. Yeah, so usually, yeah, sound, remember, is a vibration. So sometimes you can feel sounds too. That's why, like bass, you can feel the bass of music if your neighbor is playing their music really loud. So right here, a cello and a violin can be about the same volume or amplitude, but have different pitches, right? So you could have a low pitched where there's not many waves, low frequency, or a high pitch where there's many waves, high frequency. Okay, go ahead and give me a green check, orange X if that's beginning to make sense. Again, frequency is the number of waves, pitch is what you observe, and amplitude just changes the volume. Okay, so you can still have the same frequency and pitch with different volumes. That's okay. That doesn't break any rules. Great. All right, let's go ahead and double check this.
Here, use your thin lines with the whiteboard tools. All right, we're going to match up the terms amplitude, frequency, and pitch. So which one is going to be the number of cycles in 1 second? What is the perceived highness or lowness of sound? And what is the height of wave or how loud the sound is? All right, looks like we're pretty good on this. So this is going to be number three in our notes. Amplitude is just the height of the wave. The frequency we learned kind of like towards the beginning. Remember, that's the number of cycles in 1 second. And then the pitch is just the perceived highness or lowness of sound.
All right, everyone, let's go ahead and talk a little bit about sonic booms. All right, so sonic booms are pretty cool. When an airplane travels faster than sound, then the sound waves cannot get ahead of the plane. Okay, so here's the deal. Remember that the speed of sound in air is about 340 meters per second. So if a plane can travel faster than 340 meters per second, then you are traveling faster than the speed of sound. And at that point, sound begins to kind of build up behind you. All right, so it builds up in this cone shape behind the plane, and at some point, all of that energy gets released at the same time. And so that creates what's called a sonic boom, right? It creates kind of a shock wave of sound. And you can actually sometimes even see this cone of energy building up behind the actual plane. Yeah, the high-pitched ones do hurt a little bit. So I'm going to go ahead and show you a quick video of this one. Where did my videos go? Hold on, grab that. So that we can see that sonic boom. So here we go, sonic. All right, this one is definitely a little bit loud, so make sure that your volume is modulated. All right, here we go. Yeah, super cool, right? I think it's really cool. Yeah. All right, so yeah, sonic booms are, again, they tend to be with really fast planes. This is number 4. Go ahead and fill in the first blank with the word cone and the second blank with the word shock. All right, so again, it builds up in a cone and then creates a shock wave. 20 seconds, fill in those blanks.
20 degrees Celsius, that's just standard temperature, will need to move faster than what speed to create a sonic boom? All right, so we're working with, let's pay attention to this part. Underwater at 20 degrees Celsius, right? So where on this chart do we see water at 20 degrees Celsius, right? And then what speed would it need water? Thank you, Angelina. Yeah, meters, 1,482 meters per second. A lot faster than air because in water, sound moves faster than in air. All right, so that is going to be our answer for number 5 in our notes. Go ahead and mark that in your notes. Raise your hands, and then same as before, we'll move on from there.
Oh yeah, so okay, sorry, yeah, this is number 6, and then we'll do number 5 in just a moment. I apologize, this is number 6. Yeah, sorry about that. When I make the quizzes, sometimes it's very sensitive, so every once in a while something gets dragged where it's not supposed to get dragged to. Anyways, all right, so we know how fast we need to go in meters per second, all right? But when we talk about really fast airplanes, we actually talk about them in terms of Mach. And so there's a way for us to convert from meters per second to Mach. So to determine the Mach number at which an object is traveling, we can convert from meters per second to Mach using what is called a conversion ratio, which we write in the form of a fraction. So we know that 1 Mach equals 343 meters per second. This is just a measurement. This is how we've determined what Mach is. But here's the thing, you can actually put that into fraction form and make a conversion ratio. Now, the reason this works is because 1 Mach divided by 1 Mach equals 1. All right, so anything divided by itself equals 1. Smiley faces, emojis in the chat if that makes sense. 1 Mach divided by 1 Mach just equals 1. Okay, great. Now, the thing is, though, again, we just said that 1 Mach is actually the same as saying 343 meters per second. So I could actually plug that in, and this still technically equals 1. Now, I know 1 divided by 343 doesn't equal 1, but 1 Mach divided by 343 meters per second does. This is like saying 12 eggs divided by 1 dozen. That still equals 1 because 12 eggs and 1 dozen are the exact same thing. Same thing, if we did 343 meters per second over 343 meters per second, obviously that equals 1. However, again, we can actually substitute in 1 Mach for 343 meters per second, and that technically still equals 1, right? 343 meters per second is the same as 1 Mach, so it's still the same as dividing by itself, and therefore still equals 1. So these are what are called conversion ratios, where we have one unit on top, the other unit on the bottom, and we can use conversion ratios to convert between different types of measurements without changing them. All right, so I know it's changing their units, but it's not actually changing their identity because, again, these conversion ratios all still equal 1. Now you're probably like, I don't understand what that means, Miss Larkin. We need to practice it, so we're going to practice it in a moment, and it'll make more sense once we practice it. First off, this is number 5 because we accidentally flipped number 6 and 5. So this is a conversion ratio. Fill in the blank ratio for number 5. Thank you for all of those that caught that error and spoke up about it. 30 seconds, fill in the blank with ratio for number 5 and raise your hands. So let's go ahead and figure out how can we get from meters per second to Mach. So we just learned that the sonic boom underwater, we have to move faster than 1,482 meters per second. But that doesn't tell me what type of plane would be able to move this fast. I want to figure out what Mach plane do I need to move this fast. So what we're going to do is we're going to start off with what we know. All right, so tell me in the chat, where do you see a number in this equation? All right, go ahead and tell me what number do you see in this equation. When we do conversions, we always start with the number that we see here. Go ahead and tell me in the chat. Not a trick question. What number do you see here? Thank you, Angelina. Awesome, yeah, so this is what we know. This is what we're going to start with. So we start off knowing that I have a number here, 1,482 meters per second. All right, and I'm going to go ahead and use a conversion ratio to change it into Mach. Now, just so you know, whenever you do conversions, it's a lot easier if everything's in fraction form. So to change this number into a fraction form, we just put it over the number 1, because anything divided by 1 is still itself. Smiley faces, emojis, if that makes sense. Okay, so this number divided by 1 is still this number. Doesn't change anything. Cool beans. Now, when you figure out how to convert something, the problem is we want to get rid of these units, meters per second, and we want to change them into Mach. So the way in which you use a conversion ratio is that in the first step, wherever your units are in the first step, in the conversion ratio, they need to go on the opposite side. So currently meters per second is on the top in the first step. So where should it go in the next step? What would be the opposite side, the top or the bottom? Yeah, so it starts on top. Where does it go in the next step to be on the opposite side? Top or the bottom? Yeah, it needs to go on the bottom. So we're going to go ahead and just stick meters per second here on the bottom. Nothing with numbers yet. We don't need to worry about numbers. We're just looking at the units right now. So eventually, that's going to get rid of our meters per second. We said that if they're on opposite sides, that gets rid of them. Okay, so that's cool. However, I still need the units that I'm solving for. And tell me in the chat, what units am I solving for? What units am I solving for? I want to know what kind of plane in what units would be traveling this fast. Yeah, we're trying to change it into Mach. Exactly. So on top, I'm going to put the units that I'm solving for, which is Mach. Awesome. All right, so based on this, I need to go ahead and figure out which ratio I should use here. And these are the two ratios that we came up with earlier. Point for me on the board, which of these two ratios on the left or the right has Mach on top and meters per second on the bottom? Which of those two ratios should I use? Which one has Mach on top and meters per second on the bottom? I see 2 purples on the board. Let's get some more people up there. Beautiful. I agree. Yeah, so we're going to use this one right here on the left. Okay, so I'm going to put 1 Mach over 343 meters per second. Okay? All right, go ahead and give me a green check, orange X if you're following along so far. Again, I know this is kind of a new thing, so that's why we're practicing it together. It's kind of one of those things where you just have to practice it a few times, and then it begins to make more sense. Cool. All right, so now all we need to do is do a little bit of math. And this math is easy because when you multiply fractions, you just multiply the tops together and multiply the bottoms together. So on top, I have 1,482 times 1, which equals what? Tell me in the chat. Yeah, anything times 1 should still equal itself. So on top, I should have 1,482. Good. And what about on the bottom? What is 1 times 343? Well, yeah, exactly. It's just 343. All right. Now, this is a fraction, but remember that fractions are actually just division in disguise. So what I can actually do is I can just take this top number and divide it by the bottom number. So let me go ahead and share with you what that looks like. All right, so we've got 1,482 divided by 343. And so my answer should be 4.32. So jumping back over here, 4.32 is going to be my answer here. However, I still need to figure out what my units are. Okay, so taking a look back at our units up here, the only units I have left over are Mach, right? I got rid of meters per second, so all I have left here is Mach. And is that what I was solving for in my problem? Was I supposed to be solving for Mach, yes or no? Yeah, absolutely. So if I have a 4.32 Mach airplane, then this airplane underwater could be traveling fast enough to create a sonic boom. Maybe not an airplane, maybe a submarine, actually. All right, this is number 7. In the first box, please put 4.32. And in the second box, please put Mach.
In chat, an object in helium gas would need to move faster than what speed to create a sonic boom? All right, so with helium gas, looking at the table, right, what is the speed of sound in helium gas? Can I get that in the chat? And remember, don't forget units, right? So what do we, guys? Yeah, it's going to be 1,007 meters per second. All right, so with helium, that seems like it's a lot more denser than the air that we are breathing in right now, because with our air, right, it was around 300. This is 1,000 meters per second. All right, so a lot faster. So that's going to be our answer for number 8. Go ahead and raise your hands when you're ready to move on from this question.
Cool. All right, so let's do the same process. All right, so this time we're going to start off with a different number that we know. Tell me in the chat, what number do you see in the question? So we want to know what is 1,007 meters per second, sonic boom in helium in Mach. So 1,007 meters per second in Mach. So what's my number here? What's my number? Tell me in the chat. Again, whenever we try to convert things, we always start with what we know. Yes, I see Kalina in the chat. Yeah, so we're going to start off with 1,007 meters per second. I want to turn this into a fraction just to make my life easier. So what number should I put it over to turn it into a fraction without changing its identity? So I just put it over what number? Anything divided by what is still itself. Yeah, put it over 1. Perfect. Now, I need to get rid of meters per second, this unit. So in the next step, where should it go? Think about which side is the opposite. Should I put it on top or the bottom? If I want to get rid of meters per second, which is on top here, where does it go in the next step to be on the opposite side? Let's get some more participation. Again, I want to dismiss you as soon as possible, but that requires lots of participation. The faster we participate, the faster I can dismiss you. Yeah, it needs to go on the bottom. So meters per second goes on the bottom. And what I'm solving for goes on top. So again, what units am I solving for? I'm trying to look at airplanes that are moving in what units? Take a look at our question. What units am I solving for? Yeah, exactly. I see Mallory in the chat. Angelina, yeah, we're solving for Mach. Excellent. So again, taking a look here, which fraction should I be using? The left one or the right one? Just tell me in the chat, which of my fractions has Mach on top and meters per second on the bottom? Yes, the left one has Mach on top. So I'm going to go ahead and fill in those numbers. 1 goes on top, 343 goes on the bottom. Now, just math time. So on top, we have 1,007 times 1. Tell me in the chat, what does that equal on top? What is 1,007 times 1? Yeah, that's easy. 1007 times 1 is just 1007. Excellent. And on the bottom, what is 1 times 341? What is 1 times 341 on the bottom? Yeah, that just equals 341. So let's do the top divided by the bottom. Grab a calculator. Tell me in the chat, what is 1007 divided by 340? Sorry, that should see 343, not 341. Where am I getting this 1 from? Yeah, I believe you actually should be rounding up, right? So 293 or 2.94. 2.94, I believe. All right. And you're right. This would be Mach 2.94. The reason that my units here are Mach is because, again, we get rid of anything that's on the top and the bottom. So meters per second's on the top and the bottom. I'm just left with Mach. And tell me in the chat, is that what I was supposed to be solving for? Yes or no? Was I supposed to be solving for Mach? Yes or no? Always go back and check that your answer actually answers your question. Yeah, so 1,007 meters per second is the same as a 2.94 Mach airplane. All right, so that's going to go ahead and be number 9. First box is 2.94, second box is Mach. Go ahead and raise your hands. And then this last question you'll just need to do on your own. And we will dismiss you as fast as we can. Here we go. Raise your hands for number 9.
All right. Please don't post any answers in the chat, though, because this is a complete on your own. If you do need help, though, we are in the Q&A chat. So it is an object in krypton gas. It would need to move faster than what speed to create a sonic boom? So that is the question. Determine your answer from the table. And raise your hand for this last question when you are finished. All right. If you haven't already, go ahead and submit your notes. If you still need questions toward the end here, just stick around for a little bit. Everyone else, go ahead, log yourselves out. Have a great weekend. We'll see you again on Monday.